Hello students, this is the last one, video 21D. Congratulations for sticking it through. I hope you enjoyed the course. We've tried to make it as engaging as possible. I do want to say on video, I got to thank Kim Shepard for sticking this big project out with me. I got to thank John Clement for sticking around on Friday afternoons and videotaping last semester. Thanks to Dan Krakowski for lending us a video camera, teaching me how to use it. Thanks to Adam Giacano for teaching me how to use iMovies to get these things uploaded to YouTube, and thanks to Sue Price for teaching me how to use Blackboard. So big thanks to everybody. Here's the last topic of the whole course. Testing for a difference. Kim Shepard told you about independent samples, then I did an example, independent samples, and then she did a couple more examples. The last video is about dependent samples. We have paired data, so sort of like a before and after problem where you have two measurements on the same individual is one example. So, dependent samples, or testing means when working with dependent samples, you're going to have pairs of data values. Simply take the difference for each pair. You take your two values and you subtract them. So for instance, if you were doing a weight loss study and the same person was weighed in at the beginning and at the end, say their beginning weight was 215 pounds and say their ending weight is 200 pounds, you would take the difference. It'd be 15 pounds weight loss. That's your data value. You take the two and you combine it into one by subtracting. Once you take the difference for each data pair, you just simply run a one-sample t-test, which is the lesson 20 material. These are easy. You already know what to do. You just have to realize that you have paired data, subtract each pair. Now you have one column of data. It's just the differences, and run one-sample t-tests. And you can even compute a one-sample t-interval. So all the new material has been covered. It was in videos A, B, and C. Now we're just going to one little twist on something we know how to do. Here's the first example. We've got two. Assume for Math 127 that the first take-home quiz, quiz 1, and the second take-home quiz are equally difficult. Your instructor thinks that grades for the second quiz should be a little bit higher because students, they've had one in the bank, they can adapt to teaching style, they sort of know what to expect, and so we might expect that quiz 2 scores are a bit higher than quiz 1, presuming they're of equal difficulty. Suppose we took a random sample of 30 students from a recent spring semester. You can see the data in the notebook. I don't have the whole columns here on the slide, just the first few rows. Student number 1 got an 83.5 on quiz 2. Got an 85 on quiz 1. The difference, since I'm presuming quiz 2 should be higher, I'm going to put that number first. I'm going to subtract away quiz 1. And that student actually did 1.5 points worse on quiz 2. Okay, no sweat. Second student got a 64 on quiz 2. I guess that's an improvement from the 59, so 5-point improvement. And for all 30 students, right, here's a pretty good student here. I got 100 on quiz 2, 96 on quiz 1, difference is 6. I realize these are paired data values. This is dependent, two-sample dependent. All we're doing is run a t-test on that third column. Easy as that. A few questions to answer. Let's see, A, B, and C. I guess they're on the side of the page there, so I'll write them kind of over here. I'll leave this up. Part A says this. You can see it in the notes. We've got two samples. Explain why these are dependent samples. So for part A, it's the same student. Right? Same students, and we've got two scores. It's dependence. Clearly these are linked up, the two test scores. Right? So the variable that we're working with is the difference. The variable is quantitative, it's a test score, and the variable would be quiz 2 minus quiz 1. And that's that third column, that's the difference. Difference means subtract. Okay? Part B, you can see it in the notes. We'll run a one-sample t-test on the column of differences. What are the appropriate hypotheses? All right, let's read the problem again. Assume the quizzes are equal difficulty. Your instructor thinks that grades for quiz 2 ought to be higher on average. So, H sub 0. we're testing a mean. I'm just going to put subscript difference here. If there's no difference, then that's 0, right? So h sub 0, the mean difference equals 0. We'll assume that quiz 2 and quiz 1 are of equal difficulty and that students do no better on the first or the second. That's saying that the difference is 0. We're looking for a positive difference. So mu difference greater than 0. The way that I've subtracted them, I'm testing that quiz 2 are on average higher. So when I do quiz 2 minus quiz 1, I should expect to get positive numbers, and so positive means greater than and 0. Kim was mentioning in the last video, could you subtract in the other order? You could. Then you'd be expecting negative differences if indeed quiz 2 is harder, and you could run this as a less than test, and it's just more complicated. So make it easy on yourself. Down at the bottom, part C, I'll put it here. We trust. By now you could calculate the appropriate summary statistics. It is the last video. It's probably 2 days to go in the whole course. If you pop the column of differences in a column, you don't even have to type in the 2. You know, we've calculated these differences. You can put this in a column. You could run summary statistics, and here's the important ones. Y bar, the average difference, turns out to be about a 0.517. So, on average, the second quiz scores were about a half point higher than the first quiz scores, if I averaged out each student's increase or decrease. The standard deviation for these is about 6.115 points. Okay. Now you can put subscripts like Y bar for the difference, or with a D, or I've seen a bunch in different textbooks. Really, this is a t-test, so you know, I'm testing for no difference versus a positive difference. Think to yourself, does this seem statistically significant? Like, are you blown out of the water that the quiz 2 scores were a half point higher? Is that going to allow you to conclude that students do better? Plus, that standard deviation is sort of big compared to the difference. So, my sense is telling me this is fail to reject, but let's run the test. All right, A and B and C, we're done. Let's flip here to C and D. All right. So you're on the next page now. There looks to be, yep, plenty of room to write. Let me make a little space. Part D says finish running the one sample t-test on the column of differences. Make a conclusion in context. All right, we've got to get that test statistic. It's a t-test. The conditions are met. We're presuming these are unbiased samples. We're presuming that 30 is less than 10% of all students taking statistics. We're presuming what? I've got a sample size of 30. I should check the picture. I should check the graph. But I have enough data to proceed, right? Variables quantitative. Everything's met. Test statistic, T. Formula is Y bar minus mu sub 0 all over S divided by square root of n. Those are the numbers. I'm going to take the 0.517. And what am I subtracting? I'm subtracting off 0. That was the number up in the null hypothesis. Could we test for, say, a 2-point improvement? Like, let's say I wanted, is quiz 2 on average 2 points better? I would subtract off 2, and that number 2 would show up in my null hypothesis. Typically, we're testing for any difference, so that's going to be 0, and then S over root n. All right, numbers are going to look like what? 0.517, subtracting the 0 from mu sub 0, divided by 6.115 over square root of 30. Shouldn't be too big of a test statistic. I don't feel like this is much of a difference. 0.463. And since this is a one sample t-test, degrees of freedom is just sample size minus 1. It's n minus 1 makes 29. So let's just say in words what this means. Our sample average difference of about half of a point, 0.517 of a point, is about it's about 0.46 standard errors above no difference. It's not unusual, right? Not unusual at all. Oh, we can squeeze the p-value up here. All right, here's a t-curve, degrees of freedom, 29. T-curves are centered at 0. I'm going to shade from 0.463 and up. It's going to fall pretty close to 0. That's my test statistic, 0.463. I would use, of course, the StatCrunch tool to get that p-value. Go to the t-calculator, plug in degrees of freedom, shade up from 0.463, and you'll get a p-value of 0.323. We're experts at this by now, right? Under any circumstances, this is fail to reject. There's really no evidence that students do better on quiz 2 than they do on quiz 1. All right. Let me see. Do I have a blank slide here? I guess I do. I'll clean this up. Let's make a decision and a conclusion and move on to the very last problem. Let me peek at the notes, make sure I'm not forgetting anything like what kind of error could we have made or any of that kind of stuff. Nope. All right. Decision. P-value's large, failed to reject the null. Run it at alpha 0.05, 0.10, you're always fail to reject, right? This is bigger than 10%, so p-value's large. Fail to reject HO. And always write a concluding remark in the context of the problem. And so what can we say? There's no evidence. Fail to reject. So started off, there's no evidence. There is no evidence. I mean, what are we saying here? There's no evidence that students do any better on quiz 2 compared to quiz 1. I think that covers it, right? There's no evidence that students do any better on average on quiz 2 compared to quiz 1. There is no evidence students do any better on average on quiz 2 compared to quiz 1. You might say, well, hey, Coop, what, do a confidence interval here? We could. The thing is, we failed to reject. So there's not a natural question like, oh, by how much do they do better? Because there's no evidence that they're doing any better. So a confidence interval would cover that number 0 that would support that there's no difference. But the values you get, like, who knows what, -2 up to +2 or whatever, I don't know what that's really going to tell me in this case. So I don't see a point to do a confidence interval. But you could, right? You could. Okay. One more problem to go. It's the very last problem in the whole course. And here it is. Example, metals in drinking water affect taste, and very high concentrations of metal in drinking water can be harmful. One river which supplies drinking water to a town had 6 river locations selected. They were measuring zinc. The zinc concentration in milligrams per liter of water was measured at the surface and then at the same spot down at the bottom of the river. The 6 pairs of data are provided in the table. You can see the numbers. Do we have evidence that the true average concentration in the bottom water exceeds that of the surface water? So just think about this. There's a river. We're going to 6 different spots, and at each spot we're taking 2 measurements, surface and down at the bottom. Here's the data. I've got zinc at the bottom. I've got zinc at the surface. Let's read this question one last time. Do we have evidence that the true average concentration in the bottom water exceeds that of the surface? So the bottom number should be bigger. At least that's what we're testing for. So we should subtract. We should take bottom minus surface, right? We should take bottom minus surface to get our measurements here. And so when I subtract, I'm doing a 0.440 minus 0.415. And that difference will be positive because this one's bigger than that one. And so that difference is 0.25. And I guess this is one data point that's sort of pointing in that direction that, right, there is more zinc at the bottom. This is a positive difference than compared to the surface. All right, we'll just you crank these out on your calculator. I'll tell you the answers here, although I'm very slightly concerned with one number. 0.256 minus 0.238. This will be a 0.018. 0.177 for the third column. Fourth column, 0.121. Fifth column.
That 0.605 in the notes is 0.632.
See, we have one tiny little discrepancy. So in the notes, this probably says 0.632. And if I subtract them, I get a 0.075.
Correct.
All right. 0.716 minus 0.609 is a 0.107. I'm wondering if my camera person is going to crank these in the TI real quick and see what happens. I hope we don't have this major typo on the very last example. I'll stall for time here. I have a sample size of 6. That's pretty small, so what would you do? Remember what we're going to do. We're going to run a t-test on the differences. We're going to run a t-test on the differences. This column here, or excuse me, this row. When I run a t-test, I need some...
That's what you have there, correct.
Okay, good to know. Thank you, by the way. T-test for the differences. Sample size is tiny. We would definitely need to check for normality. And I did. I'm just not saying this for the video. I did type these into StatCrunch. With 6 data values, you're not going to see much of anything on a histogram. The QQ plot at least looked fairly straight with 6 dots on it, and so we're going to just, the QQ plot was okay to proceed. Your common sense has to kick in here. Sometimes in practice it's really hard to get lots of data, right? So we only have 6 data points, and any conclusions we make really do need to be taken with a grain of salt. I mean, there's hardly any data here. So we're going to run through the test, make a conclusion, but with n equals 6, always using caution. All right. If you type these numbers into StatCrunch and run summary statistics, we're believing that we'll get an average difference. The y bar of the bottom row is 0.0872. And we're looking for a difference, something bigger than 0. And you might say, hey, cool, this is like so close to 0, aren't we done? I mean, it's 0.088 roughly, 0.087. You've got to run the test because the standard deviation here is tiny. S equals for this problem 0.0607. So these differences are very small, right? It seems like there's always a little bit more zinc at the bottom compared to the surface. And so I'm not very far removed from 0, but in terms of the standard deviation, this actually might be a significant difference. Okay? So we've got the summary statistics. All we're running is a t-test for this bottom row of differences, and let's do it. Flipping the page, it says run the appropriate test. showing all steps. And so we have paired data. It's two samples paired. Let's see here. We've already sort of checked the conditions, at least verbally, so I'm just going to get right to it. H sub 0 versus H sub A. We'll presume that the mean difference is 0. There's no difference between surface zinc and bottom of the river zinc. The way that we subtracted them, it's a greater than test. We said, is there more zinc at the bottom compared to the surface? And so that'll be a greater than because we subtracted bottom and then subtract off surface. All right, test statistic. I have to apply these statistics here into my test statistic formula. And so the T will equal, it's y bar minus mu sub 0 over S over root n here. And if I plug the numbers in, I get a 0.0872 for y bar. Subtract off. We're testing for any kind of difference. Divide by 0. All right, that gets divided by S over square root of n. And so down here, let's see, what was S? 0.0607 divided by square root of 6. Just one thing popped into my head. We're working with these tiny little decimals. Make sure you carry this out to a good, probably 4, because if you start rounding, you're going to get wildly different values after you do the calculations. So put that in your calculator. This turns out to be 3.519. Degrees of freedom 5, it's sample size -1, 6 minus 1 makes 5. And in terms of this tiny little difference of 0.0872, that is 3.5 standard errors above 0. And that basically is coming from how tiny that standard deviation is, right? So it looks like we'll be statistically significant here. We can get the p-value using the T calculator on StatCrunch. It's a greater than test. Here's your T model. Degrees of freedom equals 5. T model is always centered at 0. I'm 3.5 standard errors up. So this is your test statistic, 3.519. Greater than test. We're going to shade up. Comes from StatCrunch. This is the very last problem of the whole semester. You know how to get this. Or you better. 0.0085. Okay, I don't think there's a significance level in this one, but even if it was, say, alpha 0.01, the p-value is below. So we do have evidence. We're going to reject the null, and there is evidence that there's more zinc on the bottom of the river than up at the surface. All right, so I'm going to clean this up, write that out. All right, to finish up part A, decision, reject the null. On the p-value chart 5 lessons ago, this is overwhelming evidence for the alternative, and we could simply say that there is evidence of more zinc on average at the bottom compared to the surface. Right, there is evidence of more zinc on average at the bottom of the river compared to the surface. Okay, so we're rejecting, we're doing it with only 6 data values. It was pretty statistically significant, so overall I feel okay about this hypothesis test, although I'm always slightly worried with these super tiny sample sizes. All right, part B. Well, I guess we did reject, so we could ask that next question. Well, by how much, right? By how much? And that's the B. Pause the video if you don't have it. I'm going to go here. Since the difference is statistically significant, we rejected the null. Support your test results with a 95% confidence interval for the true mean difference in zinc concentrations. Formula, y bar plus minus a t number, s over square root of n. We have paired data. We're just doing it on the differences. Do not do a 2-sample t interval with independent samples. You've got to think of what kind of data do I have. Okay? So we know a lot of these numbers. I know that my sample mean 0.0872. That was from my 6 pairs of data. The t number, I guess we could get in 1 second. I do know S. S was the standard deviation of my differences. That's the 0.0607. I do know my sample size, square root of 6. Be careful, not 5, 6 there. And I could use, the t calculator, degrees of freedom equals 5 on StatCrunch. I'd be slamming 95% in the middle. It's leaving me 0.025 on both sides, and that's the t number that goes here for the confidence interval. Of course, we could just, like with our eyes closed, get this, and that's about 2.571. Now that's for a 95% confidence interval, and remember the t differs from the z pretty substantially when I have small sample sizes. If we were using z, that'd be 1.96. So you can see that with tiny sample size, it's a pretty big difference there. Plug it in here, 2.571. All right, carry this down. 0.0872 plus or minus, it's your margin of error. Calculator time, it turns out it's about 0.0637. I can eyeball this already. The whole interval is positive. That is supporting my hypothesis test where we did reject the null. If this interval included 0, we'd have a little bit of an issue because your interval is telling you something different than your test is, and they shouldn't. Kind of means you made a mistake. We didn't make a mistake. Subtract, I get 0.0235. Add, I get 0.1509. And this was in what, milligrams per liter? So these are measurements. I guess they're taking water samples and how many parts of zinc are in the liter. And so we're 95% confident. These are hard to put into words, but the bottom of the river has between 2 milligrams per liter and 15 milligrams per liter more zinc than the surface. And I guess I'll write that down and then we're going to be done. So, subtract this, try to get this to sound good. These are always tough. We're 95% confident. On average, the bottom of the river has between 0.235 and 15.1509 milligrams per liter of zinc compared to the surface. Period. Right? We're 95% confident on average. The bottom of the river has between 0.0235 and 0.1509 milligrams per liter of zinc compared to the surface. And that's it for the course. So way to stick it out. Thank you for watching, and we will see you in class.